Welcome to the flight levels. Pilots use transponders to help air traffic controllers see them. For decades, the FAA has been using radar, but now ADS-B is also being used. When do controllers use radar versus ADS-B? Or is it both? Today, we're going behind the scenes of how unravel controllers use surveillance equipment to see where aircraft are. Let's get to it. Let's start with a basic, simple overview of how radar works. Radar stands for radio detection and ranging. The basic premise is to send out radio waves in a specific direction and note how long it takes for the waves to be reflected and return. When an object reflects radar waves, we obtain two elements of data, azimuth and range. Azimuth is the direction the radar antenna was pointed. Range is the distance away from the radar station. So the data we obtain from radar is essentially polar coordinates relative to the radar antenna. Unfortunately, radar alone does not provide altitude information. Some positive aspects of radar are that it has excellent range. As long as targets are within line of sight, radar is reliable beyond 200 nautical miles. It is also a relatively simple system. However, there are also some drawbacks. As mentioned, it is limited by line of sight, so there have always been significant coverage gaps. Depending on the exact model of radar antenna, most rotate at just 5 revolutions per minute. This means aircraft position is only updated once every 12 seconds. Probably the biggest drawback is the expense of running a radar site. A radar antenna is a huge chunk of metal that rotates 24 hours a day, consuming who knows how much electricity. Many sites are located in remote areas that are difficult to access. The logistics of maintaining a huge piece of equipment, especially in a faraway area, are not trivial nor inexpensive. Now to ADS-B, which stands for Automatic Dependent Surveillance Broadcast. Similar to our discussion of radar, this is going to be an oversimplified description. The first step is for the GPS unit in the aircraft to use GPS satellites to compute the aircraft's location. This results in the present latitude, longitude, and altitude of the aircraft. Note, this is the only step where satellites are involved. ATC is not connected to the GPS satellites. With this location data, the ADS-B unit in the aircraft transmits the data to ground-based receivers. That's right, ground-based receivers. Similar to radar, ADS-B surveillance is limited to line of sight and does have some coverage gaps. Some of the advantages of ADS-B over radar include more precise location information. With location being derived from WAAS GPS, the precision of aircraft location is greatly enhanced compared to the analog nature of radar. ADS-B also transmits location updates once every second compared to once every 12 seconds. The cost of running an ADS-B receiver is significantly less than a conventional radar site. There are no moving parts. ADS-B receivers are located in remote areas similar to radar, but are much more reliable and require significantly less maintenance. One of the few downsides is ADS-B receivers have a range of less than 100 nautical miles. But since each receiver is a relatively small cost, the FAA has installed tons of ADS-B receivers to ensure reasonable coverage across the national airspace system. In fact, I would go so far to say ADS-B coverage has significantly enhanced surveillance coverage in the national airspace system. All right, so if radar is so expensive and ADS-B is so accurate, why do we even bother with radar anymore? Well, as of 2025, ADS-B is only required above 10,000 feet, along with a few locations below 10,000 feet. The FAA still wants to be able to see all those aircraft that are not equipped with ADS-B. Other than cheapskate airplane owners, who else doesn't have ADS-B that we might want to know about? Bad guy airplanes. Yep, until all of the bad guys promise to use ADS-B when they fly near us, we're going to keep our radars up and running. So, sorry, bad guys. If you want to come say hello, we will still see you coming. Okay, so now we have a general idea of how radar and ADS-B work. But how do controllers choose which source to use? Luckily, it is done seamlessly through automation. Airspace is split up into hundreds of equally sized boxes. These boxes are totally independent and unrelated to sectors. Each box has the ability to prioritize which surveillance source will be used for any aircraft within the box. Today, ADS-B is the primary surveillance source throughout the National Airspace System. That means ATC will only use radar data when an aircraft is not equipped or is out of range of ADS-B. When this happens, the next highest priority radar site will provide the surveillance data for that aircraft. The awesome result of this system is the transparency to controllers. The controller doesn't care which ADS-B receiver or radar site is providing the data. The automation behind the scenes just makes it happen. Another feature automation provides is a different target symbol when aircraft are eligible for 3-mile separation. We won't go into specifics today, but essentially, if two IFR aircraft are ADS-B equipped and at or below flight level 230, they are eligible for 3 miles lateral separation as opposed to 5 miles, which is awesome. Again, all done behind the scenes. Controllers just need to take note of the symbol each aircraft target is. So far, we've covered how controllers see the location of you as you're flying along. Next, let's walk through how your altitude shows up on controller screens. So the controller gives you an altimeter setting. You set the pressure in the Colesman window. Your altimeter is now properly set so it reads your true altitude. Your transponder reads that altitude and sends that out to ATC, right? No. Luckily, it's even more simple than that. Your transponder just transmits your pressure altitude to ATC. No adjustment knob required on your transponder. Okay, so how do controllers know you're at the correct altitude on anything but a standard day? Glad you asked. Remember those sort boxes? Those also contain pre-selected altimeter stations. Let's take a look at an example. In this example, let's say you are flying east to west through sort box number 58 at 8,000 feet. For the moment, you have been assigned the JKL altimeter of 30.01 inches and are correctly indicating 8,000 feet on your altimeter. At the same time, your transponder is transmitting your pressure altitude of 7,900 feet. The controller's computer finds the difference between standard pressure of 29.92 inches and the adapted altimeter setting, which in this instance is 0.09 inches. It then multiplies by 1,000 to get 90 feet, which is added to the pressure altitude of 7,900 to get 7,990, which rounds up to 8,000 feet. This is ultimately displayed as your Mode C altitude on the controller's screen. To take this a step further, let's continue our flight into sort box 57, which is adapted to use the MNO altimeter of 30.22 inches. This is significantly higher than the pressure of the JKL altimeter you had been on. If the controller does not issue you the updated altimeter setting, the controller's computer will now do the same computation of your 7,900 foot pressure altitude with the new 30.22 inches to get a 300 foot correction. Therefore, your Mode C altitude will display at 8,200 on the controller's screen. This is a classic example of the memory aid low to high, reach for the sky. You flew from an area of lower pressure to an area of higher pressure without adjusting your altimeter setting. Luckily, controllers are pretty good at issuing local altimeter settings as you fly along your route. Once you dial in the 30.22 setting, you see the 8,200 true altitude and descend accordingly to maintain 8,000 feet. The main reason Mode C altitude works this way is to ensure vertical separation. Since all transponders exclusively transmit pressure altitude, the difference in altitude between any two aircraft is consistent. Even if an altimeter in one plane has an error or is incorrectly set, the vertical separation between two aircraft will always be accurate. So what are some key takeaways from today's video? Mostly, get ADS-B equipped. Even if you don't fly in airspace which requires ADS-B, please stop being a cheapskate, or stop being afraid of the government tracking you, or whatever your excuse is. Not only will ATC have better surveillance to provide you services, but all of the pilots flying around you will be able to see you as well. If you are equipped, be sure to request a free ADS-B performance report every few months. It takes less than 5 minutes and only requires filling out a few fields on the FAA's website. And lastly, I hope you found it interesting to learn how air traffic controllers see aircraft through a variety of surveillance sources. Thank you for watching. Let me know in the comments if you learned anything. Share this with any of your friends who may also want to go behind the scenes of air traffic control. Make sure to subscribe to the channel and head over to flight-levels.com. Remember, don't just fly, climb to the flight levels.